Welcome to the third video in my series on electricity, and this is for people that are interested in electricity in the field of radio communications, in particular amateur radio. In this video we're going to talk about the series circuit and some basic principles of direct current, and then we'll move on to more complex topics. But before we do this, I just wanted to do a quick review. If you'll remember from the previous videos, usable energy in the form of electricity is caused by the flow of electrons in a circuit. And remember also that what's important at the atomic level is the outer shell or the valence shell of an atom. If the outer shell or valence shell of an atom contains just one or two electrons, then that material is going to be a conductor. So we talked about how gold, silver, and copper are all good conductors because they shed these electrons easily. Silver is actually the best conductor, but because copper is cheaper, it's used a lot more. We also talked about how materials that have more than 4 electrons in the outermost shell or in the valence shell are stable, are relatively stable in electrical terms, and they do not shed those electrons easily. So therefore they don't really conduct electricity easily. These materials are known as insulators, and rubber is an example. Rubber makes a good insulator. It's hard to get electricity to flow through rubber because of its characteristics at the atomic level. Finally, we talked about semiconductors, and semiconductors are atoms that contain 4 electrons in the valence shell, and these can sometimes be used to conduct electricity under special circumstances. Later, when we talk about things like diodes and transistors, we'll get into some uses for semiconductors. So they're actually very important in the study of electricity, but for right now, just remember that if you come across an atom and it has 4 electrons in its outer shell, it's neither a good conductor nor a good insulator, and it's referred to as a semiconductor. Okay. We also talked about in the previous video that fact that there are 3 basic elements of any electrical circuit, all of which are interrelated. We talked about current, and current is the flow of electrons, which is measured in amps. 1 amp is equal to 1 coulomb per second moving past a fixed point. And of course, a coulomb represents an astronomical, a huge number of electrons. It's 6.25 times 10 to the 18th number of electrons. So we're talking about just a massive number of electrons. And by the way, when we talk about electricity, it's not the individual electron so much that causes the force that we use. An individual electron actually doesn't move that far. So an individual electron, for example, may only move about 3 inches in the span of an hour when 1 amp of current is flowing through a circuit. It's the overall force that we use as electricity. So if you think of like not bowling balls, if you think of like pool balls, if you line up a row of pool balls and you hit the back ball, what's going to happen is if they're all right next to each other, it's going to immediately eject the ball or move the ball that's the farthest away from you. And that's kind of how electricity works. The individual electrons move slow, but this movement itself, the electricity that we use as energy, actually moves at the speed of light. So that's what we're talking about when we're talking about current. Another element in an electrical circuit is voltage. And remember, voltage is not the movement of electricity. It's the electrical pressure or the force that causes current to flow. You can think of voltage as a difference of potential between 2 points. You'll have one terminal that's got an excess of electrons, so it's got this negative charge. Then you'll have another point or terminal that's got an absence of electrons, so it has a positive charge. Whatever the difference in potential is between those 2 points, that's your force that causes electricity to flow, and that's voltage. Remember that this force is measured in volts, and that 1 volt represents the amount of force needed to force 1 amp of current to flow through 1 ohm of resistance. And that actually brings us to the last basic element of any electrical circuit, and that is resistance, which can be defined as opposition to current flow. And remember that resistance is measured in ohms. Okay. Closed and open circuits. And another thing that we talked about at the end of the last video, so this is still kind of just review. In order for current to flow, there must be a complete path from the negative to the positive terminal or pole, basically forming a complete uninterrupted loop. So if you think of like a loop of wire where there's no breaks anywhere in the loop, that's what you actually have to have the flow of electricity. Any break in the circuit will cause current flow to cease. And you just want to be aware that a complete path for current flow is actually referred to as a closed circuit. Here again, think of just the analogy of like a loop of wire, that it's closed. In other words, there's no point where there's any breaks in the circuit. So that's called a closed circuit. If you have a break in the circuit which impedes current flow, this is actually referred to as an open circuit. An example would be where you have a light switch that's in the off position. When your light switch is in the off position, it means that there's a break in the circuit and no current will flow. And as a result, your light bulb will not light up. Okay, let's go to the new stuff now. So that's kind of just review. Series circuits, parallel circuits, and Christmas lights. Imagine that you're Clark Griswold and you want to have the brightest house on your block, actually in the whole city, for Christmas. So you buy a string of 2,000 lights. There's only one problem. The lights are wired in series. Why is that a problem? Let's think about it for a second. We just said that for current to flow, you have to have a complete path. Well, when you have lights wired in series, what that means is if you have one light that goes out, it's going to open the circuit. You're not going to have any current flowing to the other lights either. So that could be a problem. So don't do that. Let's go to the next slide. Series and parallel circuits continue. Unlike series circuits, and we really haven't talked about parallel circuits yet, but for right now, just know that a parallel circuit is a circuit that provides multiple paths for current flow. The sum of the individual branches of current is equal to the total current flowing through a parallel circuit. And if you look at the two pictures that I have in this slide, the picture on the left shows two lights which are actually wired in series. So the total current that's flowing in this circuit will pass through each light bulb because the two lights are wired in series. If you look at the picture on the right hand side, this is actually a parallel circuit because you have two different possible ways for current to flow. There's sort of this Y that branches from the positive terminal of the battery to the first little break point there. It forms a Y. So there's two places for current to flow. It can flow through the first light or it can flow through the second light. This is what is referred to as a parallel circuit. And you can find the total current in a parallel circuit by adding up the current that's flowing through its individual branches. But we'll talk more about that later. Back to my Christmas lights. I can't emphasize this enough. So if there are any Clark Griswolds out there, what you want to get out of this video is that you never want to buy Christmas lights that are wired in series. So let's go back to Clark. He buys a string of lights. He gets a best deal in the world on them. He gets a string of 2,000 lights. And here again, they're wired in series. So he puts them all up, hammers them up all over his house. But when he plugs it in, nothing happens. Well, the problem here is that he bought a string of lights that's wired in series, and so if one of the bulbs is burned out, it's going to open up the whole circuit, and none of the lights will light up. And that is the problem with buying Christmas lights that are wired in series. So if you want to not have this problem, if you don't want to spend hours and hours looking for the burned out bulb, always buy Christmas lights that are wired in parallel. If you buy Christmas lights that are wired in parallel, when you have an individual bulb that burns out, there's other paths for current to flow, so those other lights will continue to shine, and you can go immediately to the bulb that's burned out and replace it. So don't be a Clark Griswold. Buy your Christmas lights wired in parallel. Most of them now are wired in parallel, but they used to make them very commonly wired in series. And I can remember actually trying to look for burned out bulbs on like our Christmas tree and stuff because the whole string was wired in series. Sounds like it's a good deal to buy the lights that way, but when you get home, it's a real pain in the neck. Okay, we're going to start with the series circuit just because it's one of the easier circuits to analyze. And before we start talking about solving for these different values, we want to talk about the rules of the game. In other words, these are the rules that will apply to all series circuits. And it's kind of common sense if you think about it, because we still are going to be dealing with our three elements. We're going to be dealing with current, resistance, and voltage. Now, a series circuit, so just to get the technical definition out of the way, a series circuit is defined as one that only has one path for current flow. Again, think of the Christmas lights. If you have one bulb that burns out, since there's just the one path, all of the bulbs will go out because there's no longer a complete loop for current to flow. Now, when we talk about current in in a series circuit, it's going to be the same at all points in the series circuit because there's just one path for current flow. This can be expressed in the following formula where IT represents the total current, and notice that it's equal to I1, and it's also equal to I2, and it's equal to I3. So if each one of these I1, I2, I3 represented light bulbs, the current that's flowing through each one of them would be the same. So the point to remember is that in a series circuit, the current is the same at any point uh, throughout the circuit, and that the current flowing through an individual load will be the same as the total current. All the current flows through each point in the circuit. With regard to resistance, in a parallel circuit, it's additive, so it's a little different. So if you want to find the total resistance in a series circuit, what you'll have to do is add all of the individual resistors up. So this can be expressed as follows. The total resistance in a series circuit is equal to the sum of the individual resistors. And remember here that when we talk about resistors, this could also refer, there are actual components that are called resistors, and the whole purpose of a resistor is to introduce resistance into the circuit. But remember also that all loads, whether it's a light bulb or a speaker or whatever, will offer some resistance. And so for purposes of circuit analysis, you can think of a load as sort of like a resistor. And you actually have to take, like, in going back to our light bulb circuit, you would have to take into account the resistance of each light bulb to try to figure out what the total resistance for the circuit is. This can be expressed in the following formula. RT, the total resistance, is equal to R1 plus R2 plus R3. So in a series circuit, you have to add the individual resistance values to come up with the total resistance. The same is true for voltage. So when you have voltage that's applied to a circuit, there's going to be a voltage drop at each of the loads. And the key to remember, though, is that the applied voltage, in other words, the voltage that's provided by your source, like the battery or the power company, is going to be equal to the sum of the individual voltage drops across the individual loads or resistors. This can be represented as follows. ET, where T stands for total voltage, is equal to the sum of the individual loads, the voltage drops across each load. So ET is equal to E1 plus E2 plus E3, and so on. The big thing to remember here, resistance add, so if you want to find the total resistance, you have to add the individual resistance values, and current is the same throughout all points in the circuit, and the sum of the individual voltage drops should add up to your source voltage. So those are the big rules for that you want to take into account when you're analyzing a series circuit. Let's put this into practice and look at an example. Here we have a series circuit. It's got a battery as a power source, and these two light bulbs are our loads, and they're wired in series. So what we know about this circuit is that the light bulbs are connected to a 12-volt battery. We also have an ohm meter, so we know that each light bulb, let's say we measured, or maybe it even says on the package or something, but we know that each light bulb offers 6 ohms of resistance. Now here's the problem. We want to find out what is the total current that's flowing through the circuit. We also want to know what the total resistance is. And finally, we want to know what the voltage drop is across each lamp. So by applying our rules for series circuits in conjunction with Ohm's law, we can actually solve for all of these different values. So let's see how this works in a real example. Actually, we'll be using this example. Okay, so using Ohm's law and the rules for series circuits, we can easily solve for the missing values. Remember that Ohm's law is an expression of the relationship between the various elements of a circuit and is expressed in the following formula: E equals I times R, where E represents the electrical pressure measured in volts, I represents the intensity of current flow measured in amps, and R represents resistance measured in ohms. So if we want to find the total resistance, we can simply add the individual resistance values together, because remember, in a series circuit, to find the total resistance, we just add the individual resistance values. So we know that each lamp offers 6 ohms of resistance. All we have to do is add those two values together. So our formula will be RT equals R1 plus R2, where R1 stands or represents the first lamp and R2 represents the second lamp. Then we just plug in our values and we can easily find the total resistance. So we have RT equals 6 ohms plus 6 ohms, and we discover that this circuit has a total resistance of 12 ohms. I should mention too that when you have a circuit like this, that even the electrical wires, the conductors, offer some resistance. Usually though, especially like in a lighting circuit, the resistance value, the resistance of the wire is usually so small that you can just ignore it. So while there is just a little bit of resistance that's offered by the actual wires that connect the light bulbs together, because it's such a small value, we can simply ignore it for purposes of this example. Okay, let's go to the next slide. So now we know our total resistance is 12 ohms. And now that we know that value, now that we know the total resistance, we can actually use our Ohm's law formula, which we introduced in the last video, to solve for the total current. And remember, once that we find the total current value, we'll also know the amount of current that's flowing through each lamp, since the current is the same at all points in a series circuit. So once we know the total, we also know the current that's flowing through each lamp. So we're going to take our Ohm's law formula. It's going to be E equals I times R. We know that the source voltage, the voltage of the battery, is 12, so we plug that in for E. And now we have 12 volts equals I times our total resistance, which is 12 ohms. Now what we need to do is isolate the current, the I, so that it's on one side of the equation. And to do that, we can just divide both sides of our equation by 12 ohms. And when we do that, we find that our current is 1 amp. So now we know the total current is 1 amp. We'll use this information to solve for the last unknown, which are the individual voltage drops. So once we know the total current, we can determine the voltage drops for each lamp. And the way that we do that is we take the resistance value of the lamp and we multiply it by the current value, which is going to be 1 amp. So our formula will be voltage drop 1 at the lamp will be current 1 times resistance value 1. Since the current is the same at all points in the circuit, we can just plug in our 1 amp, we multiply that by 6 ohms, and we find that our first lamp has a voltage drop of 6 volts. Now we can use our voltage rule for series circuits to find the remaining voltage drop value. We know that the source voltage is 12 volts. And we know that the individual voltage drops have to add up to the source voltage. So now that we know that the first lamp has a voltage drop of 6, we simply subtract that from our source voltage of 12 volts, And we find that our second lamp also has a voltage drop of 6 volts. This is how these different rules come into play in a simple series circuit. Series circuits are what's the word I'm looking for? They're ubiquitous. It's both series and parallel circuits are ubiquitous in the world of electronics. So while a lot of this stuff is kind of simple at first, this will help us to understand the more complicated subjects when we get into the specifics of how radios work. How does a transceiver work? How does it take electricity and take an audio signal and transform that audio signal into a how does it transmit that audio signal from one place to another. So, but to be able to talk about these more complicated subjects, we have to start here, and that's why we started with the series circuit. In the next video, we'll actually be talking about parallel circuits. I hope you learned something, and thanks for listening.